That was the wrong button. Let's try that again. Let's try that again. No, nothing happens. Nothing happens. Didn't just press the wrong button. We're all good. We're all good here. Last episode. Got to get it right. Hello and welcome to another episode of the Oxford Online Maths Club. My name's James. I'm your host this evening. We're going to do some mathematics. Shout out to people in chat. Hi to Josh. Hi to an anonymous person. Hi to somebody who's put their name as your name bracket optional close bracket, which I love. Hi to E as well, who says great series. Thanks to everyone else involved. People are already doing the thank yous, which is nice. Hi to Issy as well. He's just got here too. If it's your first episode watching live with the Oxford Online Maths Club or watching the YouTube replay as well, then this is also the last episode. Just for a little while, but the last episode in this series, season 2, we've been calling it, of the Oxford Online Maths Club. This is the 12th episode. We do 12 in a pack plus an episode 0, so I suppose 13 in a pack of episodes. Hi to everyone who's saying hi in the chat. Oh, brilliant! Look at all this. It's really getting my numbers up. It's also the last episode. But if you're new and if you're joining in for the first time and you're live, then you can join the live chat, which is appearing underneath right now over at slido.com/OOMC. Hi to Beta, hi to Anonymous. We're going to do some mathematics. There's loads of stuff that I realised we haven't covered. First, some things that I promised you I'd come back to and do on the live stream that I never did. So I'm going to try and fix all that up so we can wrap stuff up a little bit. Some of you will have noticed afterwards there's subjects that the season 2 did, which we've learnt by asking all the guests who have ever been on what A levels they did. Great, love it. What was I saying? Something else, something not important probably. Yes, okay. Some of you will have noticed that from a couple of weeks' time, starting the 5th of August, we're doing a different live project that's kind of taking the slot that this one's in at the moment. So our new Thursday 5 PM live maths show is going to be called Mat Livestream from the 5th of August. And that's going to be on a separate website and have a separate name, but you and I will both know that it's still sort of the same thing. It's going to look very similar. It's going to have me in the top corner. It's going to have chat and some maths going on. So it's got a different name. That's me trying to get more clicks on it, right? That it's got MAT in the name for the clicks. But you and I both know that that's secretly more maths with a bit more theming. Right, okay. And Mat Livestream is back, by the way. Some people who joined us last year, we started doing stuff originally when everything went online. We did an open day online, and then Mat Livestream kind of came out of that last June. Mat Livestream being back again. Raphael, I remember from chat from last year. We're going to go around again and do some more math problems, which is going to be fun. Sorry, the Pierre de Fermat comment is fantastic. I love it. It's so good. It's one of those sort of self-contained jokes. Ali already wants to know what Ali also already wants to know we're coming back next January, which I hope so. I hope we're going to be back. This has been a lot of fun, and it's been quite a good way of getting a load of maths out there where loads of people can see it. Right, I'm already doing the wrap up at the end, which is not what I wanted to do. Let's have a quick look. Will chat be as high quality on the Mat stream? Nobody knows. Depends who turns up. None of the guests ever asked what A levels you did. Sorry, chat. Chat, what A levels are you doing? What A levels did you do? Sorry, chat. Hi, Roberto. Am I selling out? I'm getting the clicks. That's not quite the same. There's no... Selling out is when you get cash, right? So, all our ad breaks are sponsored by Maths Concept. Right. Oh, MAT just means food in Norway, I've learned. Are we doing a lot of math questions? So structure for the math live stream is not all about math. Sad face. Those are two different questions that have come in simultaneously. Math live stream is going to have some warm-up problems, which are a bit more like exploring A-level material. So a little bit more familiar maths for you, but warm-up, so some exercises, but it's a little bit like revision, or a little bit like learning new stuff if you're in year 11. Maybe not new stuff, who knows. Learning some new stuff or revision, and there's some math problems, and then there's some extension material on each one, which is just not math, or something else, or something that is just there because I wanted to talk about it. Can you not do math in the Mat live stream? I've got a plan. The Mat live stream is slightly more prepared than other projects I organise, and that one is unfortunately going to involve math questions. Right, okay. Enough about future projects, those. Oh, thank you, man. You made me put there. There we go. Put some A-levels in. Those are the A-levels I did. I wonder if that's a joke, and that's for the A-levels. Anyway, it's time to press this button to show you coming up on the live stream. I thought the last one was the one where everything went wrong. Oh well. Today, a few more things that I want to tell you. I'm going to try and fit in as many things as I can. I've already wasted 5 minutes on just the next things and the previous things and the thank yous. We're going to have chaos. Now, you might think that a normal live stream run by me has chaos in it, but this one's going to have more chaos than normal. And also, we're going to go back to another tiling problem. Tom's episode with tiling in a few weeks ago was really popular. Some of that is people clicking for Tom, some of that is people clicking for interview questions, but I think some of it is people clicking for tiles. People love tiles, so I've got another tile problem. Don't step on the Matt live stream. Yeah, okay. The Matt live stream is going to be easy to find. For example, there's a link on the club page, on the Maths club page, and just if I do my job properly, then it's going to be everywhere. You won't be able to miss it. Right, okay. Right, what are we doing then? So we're doing more tiles, and there's going to be further reading posted on Friday. Let's put little quote marks around Friday. For the first time ever last week, I missed the Friday deadline. Things went a bit wrong, and I missed the Friday deadline. Really near the end. I almost made it all the way through getting it out on Friday every day, but no. Further readings posted at some point afterwards, after the live stream. Usually Friday. You can find out more about the things we talk about over there. Right. Okay. Oh, that's a nice sentiment, isn't it? Look, chat's lovely. There we go. Right, okay. Chaos. So, I want to try and tell you about a bit of maths that we haven't talked about yet. We kind of mentioned a little bit of chaos in one of the earlier episodes. Can you remember which one had a little bit of chaos in? But we're going to do a bit more. So, I'm going to start by thinking about, and this is a problem that chat can help with, solutions to, let's be spicy, let's use radians. If people don't like radians, we can stop using radians. But I've been interested in sine. I'm going to put a pi x equals x. So this is something I'm interested in, where a is going to be some real number. I think I'm probably going to take a to be some positive real number. Okay. If I put 0 in, it's kind of boring. Let's allow that maybe. Yeah, it was in the epidemiology episode. And Molly is like, not radians. Molly, I have a good solution for you. You can play along if you switch all of this to 180 instead of pi. So whenever I say pi, you hear 180. And if you do the bit with your calculator later, then that's going to be in there as well. Was the biology one where everyone wanted to ask about complex numbers? Yeah, I remember that one. Francesca's second episode had some chaos in. And people really wanted to ask Francesca about using complex numbers for biology, which is quite exciting. And there's a good opinion about radians that's just appeared in chat as well that I'll let you read on screen. X equals 0 is pretty good. Yeah, okay. So x equals 0 is a solution. Chat's already started solving this. I love it. I'm reading out stuff about math or whatever, or radian hate, and chat's already off solving this equation for me. Brilliant. I should show you more equations that I need to be solved. Yeah, I did think about gradients. So if you want to do gradients, you can play along as well, but you need to imagine that this says 200 gradients. By the way, if you've never heard of gradients before, you just learnt the only thing you need to know about gradients. That's the only thing they've got going for them. Right, anyway, okay. Anyway, I'm trying to solve this equation. Sine of a pi x equals x. And we've spotted that x equals 0. It's always a solution. I'm going to try and draw a picture to see if there are any more solutions. Wish me luck, this is not an arts live stream. Okay, I'm going to draw x. Oh, I've drawn this really wide. Let's draw x like this. It's a sort of stretchy graph, it's not equal. Yeah, okay. Let's draw x really wide, and then I'm going to try and draw... So there's a factor of pi in there, which is making, it's changing the numbers, but a times pi, a times 180, a times 200, that just means changing which positive number appears in here. So I need to think about different positive numbers. What does sine look like? So if a is, well, maybe we should try some special numbers where we can sketch this. As a increases, does the number of solutions increase? That's true. We're going to find out why. Okay, so if a is, what do I want to put in? What do I feel like sketching today? If I put in a equals 1, am I feeling brave like that? Yeah, I think I'm feeling kind of brave. Maybe I'll put a as 1 over pi in to try and cancel out that pi, right? If I put a as 1 over pi, then I get sine x. Or if you're in gradient worlds, then you need to divide by 200. Sine x is like that. Then it turns out from what I know about radians, I suppose, that sine x, for x positive, sine x is always less than x. It's just a fact I know about sine in radians. So in fact, if a is 1 over pi, then 0 is the only solution. And actually, if I make a smaller number, so sorry, that was a fact I know about. I know this weird fact about sine in radians, that it's always smaller than x. Brilliant. Yep, okay. If I make a smaller, then that's like stretching out the graph transformations, right? If I make a smaller, that's like stretching this graph. So if I make a, I'm kind of doing the boring cases first, right? Because I'm too scared to do the exciting cases so far. Okay, if I make a even smaller, then that kind of stretches everything out, and that's just more boring, right? Because there's still only 0. It's the only solution. If I make a bigger than 1 over pi, things get more interesting. I'm going to draw a new picture for that one, I think. Maybe not. Let's see if I can push my luck over here. Let's try a is, I don't know, let's try a really big number, like 1,000 or something. Okay. So if a is, Flynn is telling me about special case, x larger than 1. Something interesting happening at 1 maybe when this becomes sine pi x. I think it's kind of interesting. Mod x is going to be less than or equal to 1. Yes, that's a good fact from Ross. Ross says that if you're a solution of this equation, then x is equal to sine of something. And it doesn't actually matter what's inside here. Just because x is equal to sine of something, that means that mod x is less than 1. So actually all my solutions are going to be inside some box between -1 and 1. Brilliant, okay. Yeah, so there's a solution from somebody who's taken the username zeta of 1/2 plus it. You know, we're all for that around here. The username zeta function at 1/2 plus it, if only we knew whether that was 0 or not, suggests that this is sine a pi x is less than a pi x. So you need a to be bigger than 1 over pi. Yeah, I think that's a variant of this fact, that you need a to be bigger. Always an odd number of solutions. That's a great suggestion. The answer is yes, because 0 is always a solution. And then if x greater than 0 is a solution, so if I've got a positive number that I could throw in here, then minus x is also a solution. Now you might have spotted that from the symmetries of the graph, or you could also check algebraically that if you stick minus x in on the left, you get minus the same thing. So that's the same thing as minus x being a solution. So yes, correct, always an odd number of solutions. Ooh, right, okay. Now we've got a solution involving x equals 1. Right, okay, I sort of want to sketch my 1,000 case, just because I'm making a silly point, I suppose. If a is 1,000, then this is a sine wave that oscillates really quickly. So in particular, it would look something like 1, minus 1, 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 like that. And you could get loads of solutions. Okay, brilliant. Yep, sine x is an odd function, so you could get an odd number of solutions. I haven't drawn them in over here, maybe I should. There we go. Drawing is tricky. Right, okay. So this fantastic picture of a equals 1,000 shows that you can have lots of solutions. You get kind of more solutions at some point. It's kind of tricky to work out when you get more solutions, actually. You have to think quite carefully about how, as you stretch this, these peaks and troughs of sine come inwards, and maybe this line intersects them or doesn't, which is a little bit tricky to work out. There's a past Mac version out there which talks about how many solutions with a particular value in, how many solutions this might have. Yeah, somebody, here's some constructive feedback from chat. My picture of 1,000 looks more like their picture with 10, so my picture's not wibbly enough. I need more wibbliness for the 1,000 case. Yeah, cool. Right, good. Okay. Good. So we can get lots of solutions. And it's quite hard. I think so. There was a really good comment earlier from, was it Ragnar? Yeah, still on the screen there. Observing that, and I like this, rather than looking for values of A, you can try and look for values of X to say X equals 1 is a solution if sine of A pi is equal to 1. That's an equation we know lots about because we know when sine is 1. That will be A pi is 1/2 plus 2n pi. And now it's a bit more obvious why I've got that factor of pi in. If there are odd solutions, could the answer be of the form 1 plus ka? Yes, no, good idea for x. Well, possibly. I'm not sure. So they're not quite equally spaced. I think that's maybe what Josh's comment means. I'm not sure. Oh yeah, your name wants me to think about a equals 0 as well, which I think is it's a flat line, isn't it? Because that would be 0 on the left, and then 0 is definitely the only solution. Yep. Oh, 10 is more wiggly than my picture's not even wiggly enough to be a equals 10. Wow, okay. A really big number, like 8. Yes, George has also pointed out, and I realised this as soon as I started drawing it, that the maximum of sine should be the same in all of these cases. These are all the number 1. It's not a very good picture, team. Oh yes, n could also be a negative integer, couldn't it? Yeah, in this equation that we've got down here. So we've got 1 can be a solution, so maybe the number 1 is over here somewhere. And that's the solution for particular values of a. Why are there loads of solutions? Because surely y equals x goes above y equals 1. Yes, it does over here, I suppose. All the solutions. My pictures become contradictory, or as if it wasn't contradictory enough already. All the solutions are supposed to be to the left. All the solutions are supposed to be to the left of 1. It's fine. 1 is just over here. Oh, right, okay, we're doing another graph. Hi, Siwan. Welcome to the live stream. I'm trying to draw a graph and people are spotting problems with it. That blob is the coordinate 1, 1. All the solutions are to the left and below that point. There's a bit of line there for y equals x, and there could be quite a lot of sine curve wibbliness going on, so you could get loads of stuff. Your name would like to put a complex number in, which does make things more complicated. No complex numbers today. Okay, I've got an alternative strategy. This is going to seem like a terrible idea, and then I'll explain it, and it'll seem like a good idea, and then we'll try it, and it'll seem like a bad idea again. So your initial response is going to be correct. And then midway through, hopefully I'll have convinced you that it's a good idea. So my alternative strategy is to guess a solution, and then work out sine of a pi x, and use that as an improved guess. Okay. Ragnar has thrown me a bone here. It's not easy to draw using a mouse. You're doing well. So this graphics tablet wasn't worth it then. Brilliant. Yeah, okay, graph of sine inverse x. Oh yeah, do you want to do a sine inverse x going up the other way? That's a nice idea. Yeah, sort of flip it, reverse it, put the wiggles the other way up. Yeah, you could move the sine onto the other side. That sounds nice. And then you're sketching different straight lines against sine inverse. Yeah, works. I think it's like reflecting the graph. Oh, do you want a coordinate transform? Is a similar idea as well about stretching it so that the line, as a different phrasing of the problem where you've got like a fixed sine curve and you try throwing different lines at it, and as you make the line flatter, you get more solutions. That's maybe a better way to think about it. I think people are happier perhaps if we keep the sine wave still. You know, sines are very complicated. Let's keep the sine wave still and change which line we're talking about. That's an equivalent way of thinking about it. Okay, maybe that would make the graph easier. Yeah, I kind of imagine throwing that into Desmos as well. So sort of throw it x and do a change of variables so that we're looking at solutions for, I guess we'd write u as a pi x, and then we'd be looking at on a graph of u. This would be sine u, and we want that to be equal to u over a pi. So we're varying this is a line, u divided by a pi, different gradients of that line. Yeah, so we're going to look for look for a kind of iterative strategy. Start with some number, some guess. Work out sine of a pi x. Use that as an improved guess and just keep going. I'll slow down my handwriting as well. There we go. That's a little bit better. Keep going. And we're going to see if that gives us out a solution, which is a nice idea. Yeah, so we could ignore the pi. The pi was not super useful, I suppose. I've got the pi in because it helps me scale some graphs later on. Pi is always going to appear next to the a. It's just a slightly different name for the constant. Maybe I should have just called that number b. I don't know. Okay. Oh, your name would like to use Newton-Raphson, which is not my plan today. And yeah, okay. There's kind of a problem coming in here, isn't there? Yeah. So we're generating a sequence, and I'm hoping that this converges. Hope that this converges, because if it converges, then I'll have some sort of limit where sine of a pi x, if it's converged, then it will give out the same number, more or less, just like with a tiny error or something, but it will give out the same number, and I'll have found one that, I've got sine a pi x, and as I calculate it again and again and again, I'm hoping that will settle down and give me something where it gets closer and closer to giving me the same number back. This is not going to give an exact solution, Josh is right, because this is going to get closer and closer, it's going to converge. Hopefully it will converge quite quickly and give me lots of decimal places, which is what I want, but yeah, maybe not. Okay, hope is not very rigorous. But hey, if it converges, then it's looking like we might have numerically found a solution. Okay, so I think we're at that stage where this seems like a bad idea. Let me try and convince you that this is an okay idea. This works. This throws out solutions to a problem that I don't have an exact solution for. Lots of problems in life you don't get kind of like, you've got the quadratic formula, that's great. That shouldn't tell you that you always have formulas for solutions. There's not always formulas for solutions. This problem doesn't have a nice, write down the answer kind of thing. So in some sense, the best we can hope for is a numerical solution, like working out some digits of it, and it's just some random irrational number that we're working out. People are trying it, so things that could go wrong or be not very interesting. If this converges, it's just going to converge to one of the solutions. We just saw there are lots of solutions. But that's okay, I'll take one solution. I don't have a good way to get numbers for any of the other solutions for a general value of a, so maybe that's nice. And Collimator wants to do a binary search instead, which I suppose has some advantages, which Collimator's put in there as well. But yeah, no, I like this kind of iterative approach, I think. So here's what I could do. To check that it's converged, I could try, if I want to speed this up with my computer. So I had a little activity planned, which maybe I won't make you do, but maybe you can investigate this at home. You can do this on a calculator. If your calculator has, hang on, if your calculator, here's mine, if your calculator has an answer button, like this one, you can try this at home by typing in something like sine of number times pi times x, sort of times answer instead of x, and then it will use the previous result as the value for x. And as you keep pressing equals, that'll come back out again. Okay, so maybe this seems like a good enough strategy if it works. Rather than doing it on my calculator, I've decided we don't have time to do this on our calculators. Also, I'm very lazy. Just the process of pressing equals on a calculator feels like too much work for me today. I could get my computer to speed this up a bit. Here's the computer speed up. So computer in blue on the left. Guess lots. It can guess lots of numbers. Work out sine of a pi x for all of them. Use that as an improved guess. So look at those numbers. Keep going really fast. Hope that converges. So if all of the different starting points all end up at the same point, if they've all, you do this 1,000 times and they all end up near the same point, that's pretty good evidence that it's converged to one of the solutions. Looks good. Plot that. Okay, so if all the points join up, then that's really good. We found a solution. We can start to look for solutions to this, which is pretty good. My calculator did maths, further maths, and physics with me. I'm not sure if it came to chemistry or not. I think it maybe did come to chemistry. What are we subbing in for x? Oh yeah, we're pressing the answer button on calculator. So if you want to do this at home on your calculator, you need to type in a number and press equals, and then type in something like sine of, I don't know, 0.4 times pi times answer, and then press equals and keep pressing equals. And each time you press equals now, it's got a previous answer that it's going to use as this kind of iterative thing. It's going to use that as each time. I used to sit at the back of maths class and sit at the back of maths class and just type something with answer and then smash equals, and it sort of changes over time. So that's quite nice. Anyway, okay, iteration. You only need to check -1 numbers between -1 and 1. Actually, the nice thing about this is if you start at a different number, this is just the very first sign sticks it between -1 and 1 anyway. So you don't even have to think about the numbers you're guessing with. Yeah, you could have done could start with anything. Right, okay. I'm going to try this because my computer's so fast. I can try this for different values of a. So I'm going to do, this is kind of a loop. Oh, we're doing computer science now. This is kind of a loop thing, but where it says keep going. So do that a few times. But then outside, we can do vary a. And we can have plot that inside some sort of outer thing. So it's going to change the value of a and just try out different values of a and see what happens. Carl Frederick Gauss, not armed with a calculator in real life, but in chat has got the number 0.91022, and so have I, with my favourite starting number as well. I think that is roughly where the number is for the solution of sine of 0.4 pi x equals x. I don't know any other methods, really. I mean, I know some other numerical methods that people have got in chat, but I don't know any exact methods or kind of magic, oh, it's just square root of 3 divided by 7 or something. I don't know anything like that. But in chat, people are using the calculators to solve this. I don't even know like a good way of, it's not just you type into your calculator inverse sine of 0.4 or something. I don't know what calculation to type in, if that makes sense. I don't know a form for the answer. But if you do this process, smashing equals lots of times, you get the numbers out. It just settles down to a nice number. So that's pretty nice, 0.91022. Cool. This is the high point. This is where we think this is actually a way of solving equations that we can't solve with nice formulas like the quadratic formula. Okay, over to my computer for its starring role in today's episode. Wish it luck. Hasn't exploded yet. Might never explode. This is going to be a bit of a weird picture because it's doing two sorts of loop. I'll try and explain as it's going. Here we go. Where do I want to go? I want to go over here. Haha, here we go. Good luck, computer, you can do it. So what this is going to do is it's going to draw where it's going to have some points for a particular value of a. It's going to apply sine a pi x lots of times. They'll all settle down. It'll plot that, and then it will keep looking. It will change a very slightly, throw everything away, and start again. Okay, I hope that's what I've tried to make it do. Okay, we've got a little graph going on. And at the start, nothing much is happening because the kind of final picture it's showing me, after pressing equals lots, it's found the 0 solution. So all the points are heading over to 0. We're still below 1 over pi. But then when we get to 1 over pi, suddenly it starts finding interesting solutions, like the one that Carl Frederick Gauss in chat has found. Where's 1 over pi? There's 1 over pi. Aha! So it's just, there's some dots in the middle of the screen now. It's found, each one of those is for a different value of a. It's found this converged solution. It's really nice. It goes over there. The solution branch turns around, so it gets very near 1 at one of those values that Reginald suggested below, turns around, and things are going pretty well over here. It's finding all these nice solutions over there for different values of a. And then something a bit odd happens up here. Frame rate's gone, hasn't it? There we go. Something odd happens over here. Oh, brilliant. Has never exploded. Don't think I'll explode today. Can you see what's going on here? So down here we got that 0 solution coming out. over here it's found one solution, but then around here, rather than converging to a particular solution, it's bouncing backwards and forwards between two numbers. I've told it to run for a long time, but instead of settling down to just one number, it's found this kind of sequence of two different numbers going backwards and forwards, so that when it prints out the final picture, half the dots are on each bit, and they're about to swap places again. Not quite chaos yet. Does that happen at 2 over pi? That's a very good question. No, I think it's a bit after 2 over pi. But it's a really good question about when that happens. So at this point, it's been finding this nice solution to the equation for different values of a, but suddenly at some point, instead of finding that solution, it finds this 2 cycle instead of numbers bouncing backwards and forwards. So if you try this on a calculator with 0.8 instead of 0.4, then you don't get convergence to a solution. You don't even converge to 2 solutions. That's not 2 different solutions. That's just 2 other numbers that have this bouncing seesaw pendulum swinging backwards and forwards kind of pattern. They're not solutions. They're a different object called a 2 cycle with 2 objects going backwards and forwards. Yeah, does that happen at a equals 1? What happens at a equals 1? So people in chat with their usernames and their comments have seen something like this before. I want to show you what happens if I go to bigger a values. So the bigger values of a, the more complicated the graph gets, because it's sine a pi x with lots of wibbliness. So I'm going to do this again, but going up to a is, let's go up as far as a is 2. Okay. So new graph, different y-axis. Now a goes all the way up to 2, and again it's finding those values below 1 over pi where things converge to, just converges down to 0. And then eventually it starts finding interesting solutions to the equation, once there are some interesting solutions, I suppose, after 1 over pi. Oh, really not happy with me right now. Oh, there it goes. Something different happens after 0.8. And that's completely different to the behaviour we were seeing just before. I'm going to let it build up a bit. Look at all that. And that's my favourite bit that it's drawing right now. We're going to have trouble explaining all of this, right? So what we're seeing here is chaos. This bit is chaos. You thought the previous thing was bad. This is what chaos looks like. So the reason there are these big bands of just speckly noise is because my computer's pressing equals lots. It's iterating, but the numbers aren't settling down. So we've got this spread of numbers coming out between 0 and 1 in places, right? Over here, there's just sort of white noise between 0 and 1, and things are looking pretty confusing. As you press equals, the numbers just don't have any pattern at all. They're not settling down into anything. If someone's not following this, it's because I'm going too fast. I'm also trying to do it in a way that the Veritasium video didn't do, which is fine. Catherine says, wow, good, right, okay. Quick recap of what this picture is supposed to be. I was trying to solve the equation sine a pi x equals x. I gave my computer sine a pi answer, where answer is the previous number, and I told it to iterate that lots of times with lots of different starting points. Sometimes it settles down and just draws all of the points in the same place because it's converged nicely. Sometimes it doesn't converge to one solution, it finds 2 numbers instead, and TikTok bounces between them. Sometimes it does more numbers, more than 2, but then sometimes it has this sort of stochastic noise, this kind of chaos in between, where the numbers coming out of my computer could be anything. They only look like, over here it looks like sort of one bit, because all the points are really near each other. Over here they're all spread out, like sand thrown across everywhere. There's a more standard first example that people see called the Logistic Map, which does something a bit like this, bifurcations and things splitting into 2 and they're splitting into 4, and then chaos and chaos appearing at the top. The reason I've shown you this one rather than the Logistic Map, which is a different function, the reason I've shown you this one is because I really like the way that after the chaos, this one suddenly settles down again. and does something non-chaotic over here, and then splits to chaos again. And if we keep going, this one keeps switching back and forth between chaos and stability, chaos and stability. The logistic map example that you might have seen in a number file video or in a Veritasium video stops at 4. It just runs out of numbers that it makes sense to put into the equation. Here, as I keep changing A, this one flip-flops back and forwards between finding stable 2 cycles and stable and regions of chaos, which is, I think, pretty nice. You get these kind of tree-like structures with different trees growing out of the top. Yeah, it's like a Veritasium thumbnail. Brilliant. Is it to do with the gradient? Yeah, it's to do with the gradient of sine A pi x. So the gradient of sine A pi x tells you what's going on nearby the fixed point, nearby the solutions, sorry. And then that's pretty bad. If you do stochastic modelling at uni, is that basically chaos theory? Hopefully not. So stochastic modelling would probably be trying to find patterns from random things. This is not random. This is deterministic. If I do this again with the same starting numbers, I get exactly the same thing. There's no randomness in here. I'm not using any random numbers. It's deterministic. That's just literally the answer to what happens when you do sine A pi x on these starting numbers. That's just the answer. There's no sort of rolling dice or choosing random numbers in between. That's where the points end up. Do I work with Marcus? We work with Marcus. Marcus is on the website recently, on the main channel. Good. Okay. And chaos comes up in other places as well. Someone's mentioned Conway's Game of Life. I'll put a link in the further reading as well. Other systems that have these really simple rules. This one is just smash equals on your calculator, but really complicated outputs. I really like that as a sort of metaphor for mathematics, that you can have really simple starting points or really simple ideas that have really complicated consequences. I rushed through this one a little bit, going through the kind of equation we're solving, but getting to this kind of really complicated answer to what happens if we do sine of 2x? What happens if we do sine 2 pi x and then reapply that function lots of times? The answer is it could be anywhere between 0 and -1. Actually, between -1 and 1. I haven't shown you the full picture. Do you want to see the other half of the picture? Yeah, you do. Of course you do. The picture's actually much more complicated because there's sine can be negative numbers as well. So there's these different bits of stability going on inside there. It's actually, the first one is unusual because the first one just goes to one side. After that, there are 2 cycles going between the different sides. It's just much more exciting. This is MATLAB. MATLAB is software that we teach our first years to use. I also learned how to use it in the first year of my degree, and I haven't learned anything else, so I'm still doing everything in MATLAB. If you use higher accuracy floating points, then you get the same effect. It's not a rounding error. It's sort of the opposite of a rounding error. Anyway, it is deterministic, says Rafa, but the phrase is sensitive to initial conditions. That if you start with a slightly different number, you get to a completely different endpoint after a thousand iterations. So iterating functions, surprisingly complicated. You can get weird stuff coming out. By the way, I just really love. This has been on the screen for a little while. Maybe people have spotted this. That in the kind of white noise sections, it's not uniform. There's this sort of dark line running through it over. Can't really see that. Comes out over here and goes in over here. It's this kind of diagonal line going through the whole thing. There's some distribution in there. Does it make sense to talk about the distribution of points where everything's deterministic? So I can just say where they are if I really want to. Anyway, chaos is really fun. It is symmetric at the top, but not at the bottom. Yes, that's true, Leibniz. Right, okay, the next one up. I think all the next ones are all symmetric afterwards. I think. It keeps doing this again and again. Kind of because of the thing, Reginald's solutions. So the solutions when x equals 1 over here, they turn out to all be stable. So there's this nice periodic thing. This is a sort of nice, sensible periodic feature that comes back every 2n pi or whatever it is, comes back frequently. Everything else in between is a bit mad. Right, there are lots of little bands as well. So as well as the big bands, like these ones, there are lots of these little bands where something else stable and well behaved has just popped out of nowhere. Chaos is just not chaos for a bit, stable thing, and then it breaks down into chaos again. It's going backwards and forwards quite a lot in between as well. That's on the logistic map as well. Link in there as well. Lots of little bands of stability. Yeah, cool. What a weird picture, eh? That's just from doing sine a pi x lots of times. Thank you, computer. You did very well. And now I will let you close that massive, massive program. Frame rate might have just got better. YouTube, you all right? Everyone's happy. Good. Okay. That was a bit mad, wasn't it? So that was one thing I wanted to show you because we mentioned chaos a few weeks ago, and I thought, I've got to show them some chaos, right? The normal starting point for people to learn about that is called the Logistic Map. The Logistic Map is a sort of similar idea where you look at the recurrence relation, I suppose, like this. That's a more a sort of simpler starting point that people look at, and there's loads on it on the web, on things like Wikipedia or Veritasium or Numberphile or things like that. Why have frame rate when you can have a slideshow? Yeah, a very nice slideshow, right? I don't know how many slides there were supposed to be while the computer was running, but yeah, you maybe got at least 3 of them. Okay, logistic map, and also the thing to look up if you want to see more is chaos. Right, cool, good. Okay, second thing I wanted to show you is another tiling problem. And I had this in the further reading a while ago, but I want to talk about it because it's quite a nice problem. Here's the tiling problem. You've got a 2x(n) grid. I suppose it's like a very long, thin chessboard. Can you play chess on a 2x(n) grid? I'm not sure you can. What would you do? You'd put 2 pieces at this end and 2 pieces at that end, and then they would fight in the middle. Doesn't really feel like chess to me. Anyway, maybe you put 2. Maybe you put pawns in the front, and then they're a bit doomed. Anyway, I've overthought it. Homework problem. Can you play chess on a 2x(n) grid? Maybe you get a king and a queen and 2 pawns? Good luck. Right, okay. Yeah. Oh, double pendulum as well. Double pendulum is the classic thing that behaves chaotically, which you learn about if you do physics. My little brother's doing a physics degree. It's just had to learn about double pendulums. Pretty complicated stuff with the double pendulums, to be honest. Right, okay. You've got a 2x(n) grid. You would like to cover it with 2x1 dominoes. These are all the same size. They cover 2 squares. 2 squares that are next to each other, right? You can't chop them up. You can't split them up into different bits. Here's the question: how many ways can you do this? 1D chess is a thing, says somebody in chat. So there you go. All these extensions to I've heard of sort of high dimensional chess as being a thing. 1D chess. Do you just start with the pieces and then they take each other? Yeah, okay. Bishops and knights not really going to work very well. Yeah, your bishop is in a lot of trouble. Your bishop is going to have to bounce backwards and forwards diagonally. Cool. I understand nothing, but this feels interesting. Here we go. Okay. How many ways can you do this? So, problem solving challenge. Sometimes we like to start with smaller problems, right? It's usually a good idea, to be honest. We're going to have a general solution. Someone's probably going to type it in chat already. So I was going to type a general solution or whatever. People are already talking about recursion. I'm going to do some small grids first. So I'm going to think about things like n equals 1. If n equals 1, then the grid is 2x1, the domino is 2x1, and I want to put the domino onto the grid. There is one way to do that. I'm feeling clever. I'm feeling like a mathematician today. That's good, that's good. When n is 2, I've got a 2x2 grid, and I can put my dominoes on like this, or I could put them sideways like this. There's 2 ways. When n equals 3, I'm going to have to actually think now, I think. I think. I could put 3 vertical like this, or I could put the left ones horizontal, but then I've got to put a right one, or I could put the left one vertical and then some horizontal ones. It's going to be 3 ways. Aha! I've spotted a pattern. For n equals 1, those things are different. What are those pictures? Equals line and line equals. Is that a domino 2 different ways around? I think my dominoes are supposed to be, you know, which two squares is it covering is the only thing I care about. I know real dominoes have got different numbers of dots on, except some of them don't. I'm going to count those as the same way. If you rotate a domino but keep it in the same place, I'm going to call that the same way. People want to be... yeah, Joanna's... I agree with Joanna. Hasn't appeared. Never mind. Maybe this is n, 1, 2, 3. Sadly, the next one turns out to be 5, at which point people will start thinking of Fibonacci numbers, I think. Somebody else has pointed out that if n equals 0, there is one way, which is do not place any dominoes. But that feels a little bit philosophical, like we might not have thought of that. Some people might call that 0 ways. Yeah. I'm going to call it one way, in which case this looks more like the Fibonacci numbers, 1, 1, 2, 3, 5, 8, 13, but not like the counting numbers. So people are asking about rotating the domino. I'm going to go with not rotating the domino. If you want to allow rotating the domino, then you might also have to allow for flipping the domino over. I sort of just want to keep track of where are the dominoes, which squares are they covering up. Not, you know, you could do it with different coloured dominoes, or with, I'm being silly, you could do it with different coloured dominoes. I don't really care about what the dominoes are like, just about which squares are they covering up. It's not quite... people are arguing about 0 factorial now. I also think 0 factorial is 1. Right, yeah, okay, but consensus maybe for this being one way. Anyway, it turns out when n equals 4, turns out there are 5 ways. Which is sort of sad, because this could have been a really nice pattern of just n ways, but never mind. Cool, good, okay. There's actually a sort of clever sub-problem way. So a sub-problem approach is when you split this into sub-problems. So you could think about case 1, top left is like this. So the top left could be like this. Or case 2, top left is like this. There's a domino here. It could be that way around, or it could be that way around. You could rotate the physical domino, but I'm counting those. It could be joined to that square, or it could be joined to the next square over. And that gives you 2 different sort of scenarios. In the first case, we've still got to do the rest. I suppose we've got to do the rest of the grid. There's now a square over here where the only way I can fill this in... Let's bring some colours in here. The only way I can fill in this square underneath is to put another sideways domino in. So this square, the only thing I can join it to is the square next to it. Okay, and now I've done the first 2 columns. So I've still got, let's go black again, still got n minus 2 to go. In the case 2, I've got n minus 1 to go. Having n minus 1 to go means that the bit I haven't covered yet it's 2 by n minus 1, and I've got to cover it. And it doesn't really matter how I do it. I've got different ways of covering it up. That means that I can write the following nifty equation. If I write an for the solution for an n grid, so there's always different numbers for how many ways there are to do it for different values of n. I could have an to be, that's going to be an minus 2 for the first case. So there's some things from the first case, if I take off the first 2 columns like this, or alternatively the top left domino is like this, and it just takes up the first column. And those cases, there are n minus 1 of those, because I've got to tile an n minus 1 by 2 grid over there. Those are all the different cases for the problem with n, so I need to add those things together for all those different ways there are to cover that grid. This is kind of like induction, right? If you can do the smaller cases, if you can do the case with 2 by 3 or 2 by 2, then you can do the case with 2 by 4 by thinking about how it's either a domino and then a 2 by 3 grid, or it's 2 dominoes at the end and then a 2 by 2 grid. Those are the only possibilities for how you do the left edge in the 4 case. So it's going to be all the ways there were to do a 3 by 2 grid plus all the ways to do a 2 by 2 grid. You just add together the previous ones. That's exactly Fibonacci. Oh, why have I started writing Fibonacci? I can do this. No, too many N's. Too many B's and N's and I's and C's. Cool, yes. Monty Chess is in. Is everything in? Nobody talks. No. keep talking, nobody explodes. That game contains everything. Oh, somebody's helpfully given me a helpful tip. I've got the N's and C's the wrong way around. Oh my word. It's like every live stream. I can't spell. Right. So that is the Fibonacci sequence, because it starts with 1, 2, or if you prefer, it starts 1, 1, and then it's got exactly the same relationship. Each term is the sum of the previous two at the Fibonacci numbers. And people in chat are going to tell me how to spell this. People have got 2 C's and 1 N. We got there. Sometimes I give them 2 B's as well, which is not really what we want. Okay, let's talk briefly about our more complicated problem. So I love this problem. It has a nice answer, Fibonacci numbers, and has a nice way of thinking about reducing things to subproblems. There's a more complicated one that I put in the further reading, which is to do the same thing, 2 by 1 dominoes on a 3 by n grid. I've got 9 minutes in the live stream. It's gone ominously dark over here. I'm going to try and do the 3 by n case. Wish me luck. If we follow the Fibonacci thing, then for n is -1, are there 0 ways? That is pretty complicated question. I don't really know what the -1th Fibonacci number is. Do you sort of work them out with the same rule? Is that the proposal? Your name optional? Right, okay. Leonardo da Pisa. Right, good. 3 by n grid. Okay. Same idea though. So this is, I quite like this because within the 2 by n problem, we do some sort of subproblems induction, like a recursion relation, to relate it back to previous problems using our knowledge of what we've previously done, building up from smaller problems. We do the same thing on a meta level to get from the 2 by n problem to the 3 by n problem. We don't take the numbers from the 2 by n problem, we take the ideas from the 2 by n problem. So the 2 by n problem includes induction on the 2 by n case, and then the 3 by n problem includes ideas from the 2 by n problem. So it's sort of like a induction through ideas or inspiration. Anyway, I've said way too much. We're going to consider which way around the thing is for the square here. This has got to have a domino on it. Once again, the question is how many ways? How many ways? How many ways to cover with dominoes? A domino being a 2 by 1 tile. Same idea. This one in the middle, on the left edge, that could be like this, or it could be like, it could go up, or it could go down. Okay. Or people are talking about, you can't fill the first column with just 2 by 1 tiles. That's right. I'm not just going to get a previous result. Maybe start from 2 columns. Ah, yeah, Ross. Brilliant comment here. If n is odd, I didn't spot this first time I tried this. If n is odd, case 1 and case 2 both work on 3 by n grid. Yes, both of these. So both the things we had before, with the top tile going like that, or the top tile going sideways. Yes, and there's also another one. If this isn't the Fibonacci numbers, I will be disappointed. Oh dear. Yeah, you cannot have. If n is odd, 0 ways. You just can't tile it if n's odd, because it's got an odd number of squares, and we've got all our dominoes have 2 squares in them. Okay, in that first case up there, I can see that we've got some little sticky out bits that need to be tiled with a domino that's going to have to line up, isn't it? We'll have to put dominoes in here. Similarly, I suppose we're going to have to put a domino in over here for this corner. But then I don't know whether this next bit is going to be like that or not. I've got to put this over here. Here's the clever idea for this case. So we could keep thinking about what's going on next to it. Are these ones sideways or are they vertical? If it's vertical, then we've kind of cut the end off and reduced it to a smaller problem. If they're horizontal, then it's a bit more complicated. We've got to a different problem, and maybe it's then one at the bottom and then keeps going, so it's a bit awkward. There's this great idea to do an for how many ways to tile a 3 by n board, and to separately write bn for how many ways to tile a 3 by n board with a corner removed. So these are two separate problems. One of them is not in the question, to do a 3x board with one corner removed. But I've seen it's this problem here where we've got one corner missing, and I don't want to go into sub problems. And over here is also what we want to do. Is the 3x(n-1) board over here with one corner removed. So this over here would say something like these different cases mean that an, the number I actually want, is equal to, well, in the first case you could chop the first two columns off and do something like an-2, tile the rest of it, or you could put tiles like this and tile the rest of the shape, which is 3x(n-1) with a corner removed, which I'm calling bn-1. Or you could do like that. That's also, this case down here is also bn-1. There are bn-1 ways of tiling the remaining space here. So there's two. There's two ways to do it, either that way up or the other way up. So double. Okay. There must be one domino that's sideways. That's true, I think. For each column. Oh, for each column? Yes, that's true. Yes. Each column's got 3 in it, so you can't just have vertical dominoes. L-shaped dominoes. L-shaped dominoes, brilliant stuff, love it. Different time. Okay, separately, so that's a kind of fact, but I've kind of cheated by bringing in this bn thing that we don't really care about, and I don't really know anything about it. So now I've got to think about bn. So that's this problem with a corner removed. So there are two cases here. We can think about this one. This could have, so this is my bn problem, where I've got this square here could be tiled like this, or it could be tiled like this, vertically. Okay, it could be tiled like this. So two possibilities for bn. It's either, that first case, there's a leftover bit over here, we'll have to put a tile in like this to satisfy this square here. And then what have we got? Well, then we've got, we've got a leftover tile over here as well, haven't we, actually? Because this one is only touching this. So then that'll be, there's a bit involved. If we put a tile in the middle like this for the bn problem, then we just have to fill in this tile here and this tile up here to make sure that we're covering all the rest. They're only connected to one remaining square, so those dominoes are forced. Then we'll have bn-2 because I've taken off 2 rows and I'm doing this problem, bn-2 with a corner removed, plus over here if I just put a vertical tile, then that's an-1. Phew, okay, this is actually brilliant news because I've now got 2 equations for 2 sequences. This is pretty good. Why was that -2 instead of -1? Because I've taken 2, over here it was because I've taken two columns off, and over here it's also because I've taken 2 columns off. I've taken off bn-1 would be if I had to do just 1 fewer, but I've taken off 6 squares. It's got two narrower. So it's bn-2. Your question was why is it an-2? And this was an-2 because I've taken off 2 columns, 1 and 2. So if this was n, then the remaining chunk is n-2. Okay, good. Brilliant, I've got 2 equations. I can actually solve these like simultaneous equations. It's a little bit involved. Maybe I won't do all the details. But if you can write something like this, which then if you change all the subscripts by adding 1, so it's the last one and I know I've lost everyone, but that's alright. You can rearrange this one to get an expression for bn in terms of the ans, and then plug this in over here to get an expression for an. Take this, plug it in, get a kind of recursion for an. And then there's some techniques for solving recursion relations down the end, which gives you something that's not quite the Fibonacci numbers, but is a bit like Fibonacci numbers. If Fibonacci numbers means Fibonacci numbers, but different. Okay, I hope that was chaos enough. That bit was also chaos, wasn't it? Tiling problems, recursion relations, things that relate to previous sub-problems. A way to build up from smaller sub-problems. Sometimes, the lesson here I suppose is, sometimes inventing an entire new class of sub-problems that's kind of unrelated to the thing you want to find is a good idea, because sometimes you can use that in parallel to solve 2 problems at the same time. There's some of that in maths. Once you learn about complex numbers, it becomes easier. If you've got a problem with a cosine in, it's sometimes easier to switch to complex numbers because then you get a solution with sine instead for free. So sometimes doing sine and cosine at the same time is like that. Oh, we got a fun fact of the week from Molly. Thanks, Molly. Matt Parker shares a birthday with Ramanujan, both the 22nd of December. Wow, that's a good fact. Is Matt Parker here today? Not sure. Okay. We're at about time, aren't we? About time to wrap up. And everything's died. Computer's gone. Nope, still here. I'd like to finish up with a few quick thank yous and some more stuff. Forgot about these slides. Here are more things that we forgot to tell you about that I'm going to go really quickly through. Things that we should have mentioned. And if we do more maths like this next year or sooner, then other things I should tell you about. Really want to tell you about. Don't want to give you the impression that we've covered all of maths. There's loads more maths that you might be interested in. Stuff like abstract algebra. We never really got into kind of vectors and matrices and abstract versions of what it means to multiply in general, including group theory. I put some weird bits of group theory in. The original MS Paint adventure with the crossed up braids was secretly some group theory. I think I showed you the triangle with a smiley face at one point, and we did some stuff with symmetries, but we never really went into group theory as its own thing. Didn't really tell you anything about logic and set theory. That's quite important. It's quite a big thing. We had a little bit of intersection of sets last time, I suppose, but not really going in depth into the logic. Didn't talk about convergence of series. That's quite a big thing. You know, like a geometric series, the terms, you add them up, they converge. Didn't really talk about that in general. We didn't talk about dynamics or how mechanics at university on a maths course is kind of different and kind of fun. We do things in a completely different way at university. Didn't tell you anything about that. Algorithms. Didn't tell you anything about algorithms. Also, quantum theory. Part of a maths course, an optional unit in the maths course at Oxford. You can learn about some quantum theory. We didn't tell you anything about quantum or special relativity or anything like that. Fluid dynamics, last one. Really surprised that we didn't tell you anything about fluid dynamics. That's what I did my PhD on. It's also what Tom did his PhD on. It was on the stream a while ago. Neither of us has told you anything about fluid dynamics. So amazing that we got through 26 episodes of that without me mentioning it at all. Are a little bit over time. I want to wrap up with some thank yous very quickly. We're over time, but you know, that's just how we roll. Quick shout out to our actual for real sponsor who actually gave us money, which is the University of Oxford. Not an ad break. They actually funded this happening, and they pay my salary, so that's nice of them, isn't it? Shout out to Simon Clark as well. In about 2018, 2019, I sat down with Simon from YouTube, Simon, who went to Oxford and is a physicist. Simon said it would be good if the maths department did some sort of live stream, so thanks, Simon. Good idea. Turns out was a good idea. So Simon gets a shout out in every live stream we do now. That's Simon's YouTube channel. Subscribe, I guess, for physicsy sort of stuff. And also Marilee Grady, who you haven't seen on the live stream but has done stuff behind the scenes. Thanks, Marilee, in the office for sorting out stuff to do with Maths Club. Also, Stephen Stickloss, of course, big inspiration for me, big role model. Go and get his free book. It's free and it's great. There'll be a link somewhere for Stephen Stickloss's free, great book. Right. We've had 13 amazing guests on. I counted. I'm not sure I got the number right. We've had 13 fantastic guests on who have shown you bits and pieces of mathematics that they like. We've had 9 amazing chat moderators who have been around to talk to people in chat earlier this term. But most of all, we've had you. We've had over 1,600 of you in chat talking about maths, telling us about what you're interested in, joining in with stuff live, interrupting all the time, which is brilliant. Just having that communication has been really special as a way to talk about maths while we're doing the maths. You have made about 6,800 posts at the time of the start of this live stream and left over 5,000 likes on things, which is pretty great. I think that's it. I think that's all of the thank yous I wanted to do at the end of this thing. This isn't the end. This thing's going to come back at some point. Check the club website. We might do some special episodes over the summer at some point, not on Thursdays, but at random times. It's going to go aperiodic, like the Penrose tiles. There might be some special episodes, so keep an eye on the Maths Club website to find out what we're up to. And we're going to launch the Mat live stream on the 5th of August, which is going to be a bit like this, with a different name and with more mat problems, I suppose. So I'll see you around on something else. But until then, it's been an honour and a pleasure to run a maths club with you, and I will see you around next time, whenever that is. And it wouldn't be a stream if I knew how to finish it properly. How do I... yeah, I want to go there. Bye! Nailed it.